let's continue, guys, with the lecture, okay? 1.1 functions and function notation. In order to tell you what a function is, I have to tell you first what a relation is, the relation. So in real life, as you know, when you compare quantities, you can come out with relationship between quantities, right? Two quantities, for example. For instance, as time increases, the weight of a growing child increases, right? As time increases, the market price of a computer decreases, right? Because the computer gets obsolete, new models come up, and so on. But now, mathematicians study these relationships, right, deeply, and they figure out that no matter how you come up with the relationships, with this relationship by comparing quantities, you must consider pairing the quantities up, pairing them up, right? So because of that, they came up with this definition, a relation. What is a relation? A relation is a set of ordered pairs, right? It's the structure of this relationship, right? So I'm going to consider, for example, one, a mathematical example, okay? But this can be done in reality with any objects, right? But let's consider something very basic, very simple. Let's pair up the whole numbers 1, 2, and 3 with their cubes, So I start with the number 1, I cube it. If I cube the number 1, what I'm gonna get as a result is 1 times 1, 1 times 1, 1, right? 1. If I cube the number 2, 2 times 2, 4 times 2, 8, right? 8. If I cube the number 3, 3 times 3 times 3, 3 times 3, 9, 9 times 3, 27, right? 27. So I get these three guys. Now, you may say, Professor, 3 to the third power 27, are you sure? Guys, whenever you are not sure about a result, we have in our website, I show you, right? This wonderful tool is called Desmos Calculator. The Desmos Calculator will allow us to do computation. Let's say I want to make sure that 3 to the third power is indeed 27, right? So I go 3 raised to the third power, indeed 27, right? And I'm telling you this straight because there are going to be moments where the numbers are not going to be that friendly. So we will need to use the calculator, right? You can use any scientific calculator, but also you can use the free scientific calculator available to you through our website. It's under the Desmos tab, Desmos Calculator. Great. Okay, so now let's do the pairing, right? Let's do the pairing. I started with 1, right? 1. I ended up with 1. These colors here, 1. So 1 pair up with 1. 2 to the power 8. So 2 pair up with 8. 3 pair up with 3 to the third power 27, right? 27. This collection of order pairs, that's how mathematicians called it, right? Because there is an order, you can see, right? Separated by commas within braces is what is called a relation. So this is a relation, just any pairing relation. Now, the first components of this pairing, 1, 2, and 3, they are called the domain of the relation. The domain of the relation. So 1, 2, and 3, domain of the relation. Okay, and the second components are going to be called the range of the relation. Okay, the range of the relation. All right, great. So 1, 8, and 27 are going to be called the range of the relation. Now, you know, mathematicians are minimalists, right? They like to simplify the notation. Instead of words, they choose symbols, right? So these first components, mathematicians call them input values first. And to shorten this further, they represent the simple values with the letter X, represented by the letter from the English alphabet X. They do the same with the range, right? They call the elements of the range the output values. Output values. And a symbol to represent the output values is this, Y. So this is represented by Y, okay? So X inputs, Y outputs. Great, okay. But now, think about this, right? Pairing up elements of two sets in any way whatsoever might not be so useful, right? Here I came up with a nice example, but in reality, these relations, they're not so useful. Mathematicians thought of that, and they decided to impose certain conditions to form these ordered pairs in order to come up with relations that are going to be useful, that will have some applications for us. So they call these special relations functions. A function is a relation in which each input value is associated with exactly one output value, a single output value for each input value, right? And you may say, Professor, what is the usefulness of this? Well, think about it, right? Think about time and think about location. Isn't it true that at a given time, you can be only at a single place, right? So if I'm thinking of pairing up time with location, a function would be useful, right? Right? Yeah, great. So now let's try to go back to a mathematical example. Let's try to pair up numbers using certain rules, right? Before I use cubing, let me use now squaring. Squaring. For example, -2, +2, and 3. I'm going to pair them up with their squares. Okay, just like I did this before. So I have to square -2. What should be the result of squaring -2? Anybody in the chat can write it out or can say it? Squaring -2, what do we get?
4.
Excellent, excellent. I see in the chat. Yeah, very good, Alan, very good, Khan. 4, right? 4, Professor. Yep, it turns out this guy is basically just this, right? And negative and negative positive, 2 times 2, 4. Professor, I'm not sure. No problem, guys, because whenever you have doubts, you can always go to our scientific calculator and raise -2 to the second power, but do it carefully. We use parentheses, notice how I have placed -2 inside parentheses, right? Raised to the second power, indeed +4. Great. Okay, and we're going to do it with big numbers later, so I'm kind of giving you this as an introduction. All right, 2 squared, 2 squared positive, 2 times 2, just 4, right? So let's write out 4. 3 squared, 3 times 3, 9, right? 9. Okay, so we get -2, pair up with 4, right? It's square. +2, pair up with 4, it's a square. And +3, pair up with 9, it's a square, right? And now, when I think of the domain of this function, Professor, you are calling it this function. Wasn't it the relation? Yeah, I'm calling it this function because notice it satisfies the definition of a function, right? For each input value, there is a single output value, just one output value, not 2, not 3 associated to each input value, right? Just one output value. Good. So then the domain of the function should be first components, -2, 2, and 3, right? That's the domain. But now what should be the range of this function? The range of this function will be, look, 4 again 4 and 9. When a component is repeated, you don't have to write it twice. You are dealing with sets. When you deal with sets, you represent or display the elements only once, right? So 4 and 9. Everybody follows? Not 4, 4, because we are dealing with sets, right? For sets, you just display the elements once. 4 and 9 is the range. Great. Okay, so this is a function. And again, notice that the condition is for each input value, a single output value, right? Yeah, great. Yeah, and turns out these type of relations, the ones that are called functions, are very useful. Another real example, besides location being a function of time, maybe we should write here, right? Real examples of functions for you to kind of have something in your mind. An example of functions. Location is a function of time. Right, this is one example. Another example could be items price is a function of items in a menu, right? When you go to a restaurant, for example, right? The price of each item on a restaurant menu is a function of the items, right? A dessert cannot have two different prices, right? Just as a single price, right? Price function of the items in the menu. And there are more examples, but for you to have an idea of why functions are useful. Now, moving forward, functions can be represented with sets and arrows, formulas, or tables. 3 ways to represent functions. Okay, besides this representation as a collection of ordered pairs, right? For example, if you want to represent this function, the one in example 2, using sets and arrows, you can do the following, right? This is the first set, -2, 2, and 3. You can place them here, -2, 2, and 3, first set. And the outputs were 4 and 9, right? 4 and 9, you can write them here, 4 and 9. And you can arrow them, look. -2 squared, 4, right? So -2, arrow with 4. 2 squared, also 4. So this also arrow with 4. And 3 squared, 9, right? You can see, look, 2 sets with arrows. They represent these 2, right? Yeah, so this is using sets and arrows. Now, mathematicians, remember, they use the letter X for the input value, so X here, and for the output values, they'll use the Y. And further, they like equations, right? So instead of saying square the input values to get the output values, they avoid all this wording and they say Y equal X squared, right? You see? Is the representation of the rule for this function, right? Yeah, great. Now, rule, professor. Yeah, this is representing what I said, right? Square the inputs to get the output. So this is called a rule. So this gives birth to the following: using function notation for the square function. You can think of this function as f being applied to the input value x, and as a result getting x squared, right? X squared. So this f should be the rule, squaring, right? Rule this X should be the input value. This X squared, the output value. And this should be read as, small thing, read as f of x. F of x. Okay, f of x. F of x equal x squared, right? Yeah, we're squaring the inputs to get the outputs. Great. And this further leads to a table that we can construct with the input values and the output values. How I construct this table, Professor? Well, you look at the functional notation here, f of x equal x squared, and you apply the function, the rule to each input value. F of -2 will be -2 squared, that we agreed is 4, right? F of 2 is squared, 2 times 2, 4. F of 3 is squared, 3 times 3, 9, right? And now we can translate all this information into this table. X for the first column, Y for the second column. For X values, -2, 2, and 3. The output value should be 4, 4, 4, and 9, right? Great. So guys, 3 ways to represent the function, right? Mainly, so far. Using sets and arrows, right? This way. Using functional notation, this way. And using a table. There are more ways to represent the function. I will tell you about that later. But now, guys, I want you to practice what we have learned so far. I believe practice makes the master. So I have a worksheet here. I'm gonna ask you to figure this out when you're on, okay? If you find the answers, write them on the chat so we can all know. Start with number 1. Based on the explanation, if they give you this function represented by sets and arrows, it says determine whether the relation represents a function. If it is a function, state the domain and range. And of course, if it is not a function, then you can say not a function, right? But can you figure this out? Number 1, yeah, take your time and figure this out. I see some students commenting on the chat room, which is good. There's some activity on the chat room. Very good, Alan. Very good, Khan, Jin, Julie. Great, guys. Very good. Let's analyze this. Look here. This is saying that Alice is going with. Alice is paired up with a cat, right? Next, Brad is paired up with dog, right? And Carl pair up with dog, right? Okay, now notice for Alice, Brad, and Carl, there is a single output value, right? A single output value. So therefore, then yes, this is a function. A function. And since it is a function, we can, of course, determine the domain and the range of this function, right? Domain should be the set of the first components, Alice, Brad, and Carl. And the range should be the set of all second components, right? Cat, dog, again, dog. Remember, we don't write dog twice, just once, right? Cat and dog. And that matches with B. Excellent, excellent, guys. Very good. Can you try the next, this one now? Try this one, guys. So see if we can figure this out. Same question, right? Determine whether the relation, because remember relations, they are all type of pairings, right? But just some relations are functions. So this says here that determine if this relation is a function. If not, state that it's not a function. If yes, find the domain and range. I see Julie, Lucero, Jing Jing, Hugh. Excellent, guys. I think you picked up this, right? Excellent. Very good. Very good. Great. Great. So again, if you pair them up, now you will see that it's going to be trouble. There's going to be trouble, right? And where is the trouble? Here, right? Here, I'm going to highlight this. Where is the trouble? Trouble here. For a function, you cannot have for one input value two output values, right? This is not good. So here, right? It's like for a fixed time being in New York and in LA at the same time. That cannot be, right? Cannot happen. So this is not good. Therefore, this is not a function, right? You follow, guys? Right? These type of forks, not good, right? Not good for a function. This other situation, good, right? You can share the outputs, but you cannot share the input values, right? Follow, guys? Yeah, try to kind of organize your knowledge that way, right? This still good, but this not good. Very good, very good. Not a function. Now we go into the numerical ones. Try to do number 3 now. It's gonna be tricky, but I think you will handle it. If needed, create the sets and do the arrowing, right? If not, just directly, right? But as a hint, I will give you a hint. It's a little bit tricky hint. For it to be a function, input values cannot be repeated, right? Be repeated. Because if that happens, it will lead to this fork, right? That we don't want. Yeah, very good, very good. Let's see. Let's see on the chat for number 3. For number 3. I see activity in the chat. Very good, guys. Yeah, you made my day. Yeah, Jing, Hughie, Lucero. Very good, guys. Very good. Excellent, excellent. Yep. Great. Look, if you look at the input values, right? Look at the input, and this is kind of a good strategy when the relations come as a set of ordered pairs. Look at the input values. Make sure that no input value is repeated, right? Because if an input value is repeated, it's going to lead to this awful situation, right? Look, -3, 0, 5, 6, no input value is repeated. So this is a function. This is definitely a function, right? And not only that, it's a function. And quickly I can pick up the domain as the collection of all first components, -3, 0, 5, and 6, right? And for the range, I can pick up the second components, right? -6, 5, -3, and -1, which are here, right? So that's it. This guy. Yeah, and try to remember these guys for your homework, because you're gonna do this on your homework as well, okay? Yeah, great. Let's do number 4, and then we will move on to something else, okay? So try number 4 now. A little bit tricky, but follow this hint, right? For it to be a function, the input values cannot be repeated, because you cannot be at 2 different places at a given fixed time, right? Yeah. Yeah, great. You see? Lucero, Savannah. Excellent, guys. Yeah, you made my day. Alan. Great, excellent. Yeah, Khan, also great. Excellent, guys. Very good. I think you got the strategy, right? At all costs, we have to avoid having repetitions on the input values, right? For a function, input values cannot be repeated. Yeah, this cannot be repeated. But notice 1, -3, -3. This is not good. Not good. -3 is repeated. So therefore, then it is not a function. It's a relation, but it's not a function, right? Because relation could be whatever, any pairing, but functions, for function, you cannot allow yourself to repeat your output, your input values, right? So therefore, you have to go with this, not a function, right? That's it, not a function. Very good, guys. So now let's talk about these forms. Let's talk about what to do when they give you some equation and they ask you, is y a function of x, right? This type of questions, right? We're gonna give you a good strategy to deal with this type of questions. But let's go back to a lecture and let's check this out. Method to determine if an equation defines a function or not, right? So the method is this. Given an equation in x and y, step 1, isolate y. Step 2, if each x leads to exactly 1 y, if each x leads to a single y, right? Not 2, not 3y, just 1 y, then yes, y is a function of x. Otherwise, no. Okay? So I'm going to give you an example here. Suppose they ask you, right? Given this equation, 2y minus 4 equal x squared, is y a function of x? Let's find out, follow the 2 steps, right? The 2 steps. First step says isolate y. Isolate y. Okay, so we start by rewriting this as 2y minus 4 equal x squared. In order to isolate y, I'm going to do the opposite of what this guy is doing, this minus 4, which is plus 4, right? Very good. Someone suggested this on the chat. Yeah, excellent, Alan. Excellent. Yeah, we are going there, right? Yeah, so that we start the isolation, right? 2y equal x squared plus 4. Great. What would be the final step to isolate y completely? Could you write it on the chat? What would be the final step to isolate this completely? We have to divide both sides of the equation by that y number. By what number we should divide both sides of the equation? I see some students suggesting. Exactly. Very good, Jules. Divide both sides by 2. Very good, Alan, also. Very good, guys. Excellent. Yeah, divide both sides by 2, right? Professor, why by 2? Because the coefficient is 2, right? Trying to get rid of this guy. If it's a 3, you have to divide both sides by 3, right? But this was a 2, so divide both sides by 2. And finally, you will get this. Let's distribute the division, so we get x squared over 2 plus 2 into 4 is just 2, right? It's just 2. So now, when you look at this, notice that for each x, for each value of x, exactly 1y, right? 1y, right? For each x that you put here, you will get some y. Conclusion then y is a function of x, right? Done. Example 2, for the sake of variety. Suppose they say now, given this other function, 2x plus y squared equal 1. Is y a function of x? Let's follow the method that we propose, right? Let's isolate our y, right? In order to isolate y now, this time, I have to subtract in both sides of this equation, this quantity, twice x, right? Twice x is adding. I do the opposite. I subtract twice x. This will be 0, and y squared will be equal to 1 minus twice x, right? 1 minus twice x. Now, who can tell me what is needed next to get y by itself? Y by itself. What operation? Anybody? Any comment there? Let's check. Eugene, you may by day. Take square roots, right? Take square roots. Square roots, Professor, why? Well, because the square root is the inverse operation of squaring, right? It's what will undo squaring, right? So this will take care of this and will leave y alone. But now, guys, however, doing this comes with a price. It's not free. I will show you. When this index is even, could be a 4, could be a 6. The price you pay for doing this is as follows. You have to attach here plus and minus, a square root of, and then this guy, 1 minus twice x, right? Because this guy is even. If it is odd, this doesn't happen. Okay, so let's say you are taking cube roots, you are not supposed to put this plus minus, right? It's free there, but when the index is even, there is a price you pay. You have to put the plus minus. Comments on the chat. Eugene, yeah, we're going there. Excellent. Alan, excellent comment. Yeah, then Eugene said, then y cannot be a function of x because of this. Look, for each value of x now, for each x, there is a positive version of y and there is a negative version of y, right? For each x, then here we're gonna have two values of y. Two values of y. Two values of y, Professor? Yeah, one positive, one negative. So this cannot be a function. Then y is not a function of x. Okay, y is not a function of x. Great. Okay, so because Professor? There are two solutions, Alan. Yeah, Professor? Go ahead.
Yes? I actually have a question. So is it always going to be like this? Meaning like if by any chance we have, like you said, for each x, two values of y, for that reason, like, is it always going to be like this? Does that make sense?
Meaning yeah, absolutely. Whenever you get this fork, right? Remember, for functions, for each input value, there must be a single output value, not two output values, right? But this is saying that for each x, there's going to be a positive y and a negative y. So 2, right? 2. So maybe this diagram will help. So this y is being associated to two different, one positive, one negative, right? Maybe it is here. Yeah, or even if we go back to the example, well, this means y equal the square root of 1 minus 2x, but also y equal, or usually they put minus, right? So for each x, I'm getting two y's, two different y's, right? So this cannot be, this is not a function. Right?
Okay, got it. Thank you.
Yeah, it's like, just like what we said before, right? For a given time, let's say New Year's Eve, right? In New Year's Eve, I cannot be in New York and at the same time in LA, right? Because I have to be in just one place. That's the idea, right? It's not a function.
Professor,
yeah, go ahead.
What if it was a y cubed?
Alan, excellent question, right? This is why this comment is very important. Index is even. The reason why this is failing is because of this plus minus, right? But excellent question, Alan. If this were a cube, this would end up being a function because I don't have to put the plus minus. And we will see that on the worksheet, okay? Yeah, but very good. Only when it's even is bad, right? A 4, a 6, 4 root, 6 root will lead to something that is not a function. But it's cube root, 5th root, 7th root, it would be a function. Yeah, and try to remember that for the homework. Yeah, great, excellent question. All right, great, guys. So now, remember, practice makes the master. So let's go back to the worksheet before we take the break. Let's go back to the worksheet, and I want you to do these two guys. Just to clarify, I think, yeah, these two. First, start with this guy. Number 6, please do this. Is this a function or not? So follow the steps, isolate your y, and see, right, if you end up with 2 values of y or just 1, and make your decision. Yeah, and let us know in the chat, right? Let me see, number 6. Very good, guys. Yeah, very good. Eugene, Kan, Alan, Jing. Excellent, excellent, guys. Excellent. Yeah, absolutely not a function, right? Excellent. Because when you solve for y, as the method suggests, right, you're going to end up with this awful plus minus, right? The awful plus minus, because we are taking square roots. We are taking square roots. Remember, this is even. This is the reason why this is not going to lead to a function. So here, this comes with a price plus minus. So we're talking about y equal plus and minus square root of 36 minus x squared. This is not good for a function. Okay, so you say y is not a function. Excellent. Try this, guys, and then probably we will take a break. Okay, try this number 7 now. Figure out if this is a function or not. Yeah, and feel free to write comments on the chat. Yeah, and very good, very good. Let's see. Hint, right? I'm gonna give you a hint. Hint for this guy. 3 is an odd number, right? Remember what we said for odd numbers, right? It's an odd number. Let's see. Is that a function or not? Number 7, in blue. I'm gonna write the function here, x plus y cube. Yeah, tricky, but doable. Very good, guys. Very good. You made my day. Julie, Alan, Khan, Hughie, Lucero. Excellent, guys. Excellent. I think you understood this. Very good. Look, if we follow the procedure, the method that we suggested, subtracting x in both sides leads to y cubed equals 64 minus x. Now, notice we have exponent 3 here, and this guy is odd. This is odd, right? So when you take the cube roots, right, you do not have to put plus minus cube root, right? No plus minus. That's only for even indexes. Okay, so you simply eliminate this 3 with this 3, y by itself equal to cube root of 64 minus x. For each x, there is a single y, right? Not two y's anymore. So this is a function. Very good. Y is a function of x. Try to remember, guys, this for your homework, and something for you to organize your knowledge. Always pay attention to this guy, the exponent associated to y, right? If the exponent associated to y is even, notice what happens, not a function, but if the exponent associated to y on top of the y, not on top of the x, right? Top of the y is odd, it will be a function, right? Yeah. It's good to make this association. You're going to deal with a lot of information, so organizing our information is good. Okay, to determine if an equation represents a function or not, we're good there. Now we're going to deal with this so-called graphs of functions, graphs. Turns out functions can be graphed. How can we graph functions, Professor? Here, I will tell you how. Functions can be represented by graphs. For example, we saw this square function, right? This is a square function that we're going to use a lot throughout this course. And if I choose more input values such as 2, 1, 0, -1, and -2, when I square these input values, 2 squared is just 2 times 2, 4. So 4 output value for input value 2. 1 squared, 1 squared, 1 times 1, 1. 0 squared, 0. -1 squared, -1 times -1, 1, right? 1. And we talk about this in case you have doubts. Use your scientific calculator or our Desmos scientific calculator, and you should be fine. -2 squared equals 4. Yeah, maybe I should go back to this squaring of negative numbers. Very important, guys. When you square a negative number, always use parentheses if you are using your calculator. Look here, either this or this, squaring 4, right? That's what we're writing for there. Yeah, okay, so output value 0, 1, 4. If you translate these input values, these output values into a graph, and for the input values, you take your numbers here. For your output values, you take your values here on the, this is called the x-axis, this is called the y-axis, right? You pair them up. Notice 0 goes with 0 here. 1 pair up with 1. Let's say this is 1 here. -1 also pair up with 1, so here. -2 and 2 both pair up with 4, right? So this would be up there somewhere. Let's say there. Right, so you get 4 points, 5 points in total, right? That you can connect with a smooth curve. And that, guys, is going to give you the graph of this square function, which is going to be this, right? Which is going to be this, the graph of the square function. This graph, this shape, this U shape that you see here, is called a parabola. Parabola, okay? So let me just do it nicely here. This U shape that is opening upward here is called a parabola. Okay, very important shape. Is the representation of quadratic functions, parabola. We will study these parabolas in details later in another section, but for now, try to remember this, right? Now, notice, this parabola was constructed by, you know, considering some input and output values, right? And then we connected them, right? But in case Further, when we are moving on, you need to remember this shape, right? Let's say you don't remember. Here is another applet that we're going to use throughout this course. It's called the Desmos Grapher or Desmos Graphing Calculator. Look, let's say, Professor, I'm not sure if this is the graph of f of x or y equal x squared. Well, graph it here, x squared. There you go, right? This is what I drew here, the parabola, right? The parabola. All right, great, right? So this is again in our website under Desmos tab. So use this grapher in order to make sense of things, in order to confirm that something should be true, use it. All right, great. Now, mathematicians, when they look at these graphs, they notice the following. They notice that when you graph a function, this is always true. If you draw vertical lines to the graph of the function, they will meet the graph only once. Look, once. Vertical lines meet the graph only once. This gave birth to the following. It's called the vertical line test, which says that in order to determine if a given graph represents the graph of a function, you can draw vertical lines, and if all vertical lines, they meet the graph at most at one point, then it means that you got yourself the graph of a function, right? Vertical line test, the graph represents a function if and only if all vertical lines meet the graph at most once. All right, determine if the given graph is the graph of a function. For example, this graph that looks like a circle or an ellipse. If I apply my vertical line test, notice the vertical line test fails, right? Because look, it's meeting the graph at 2 points. So this cannot be the graph of a function, not a function. Here I have a parabola, like a sideways parabola, right? Like a horizontal parabola, looks like that. But let's see if this horizontal parabola is a function. Well, if I apply the vertical line test, you will see that in general, the vertical lines will meet this at 2 points, right? You may say, but what about here, Professor? Yeah, here it's meeting at 1 point, but in general, right? Look, this one at 2 places, 2 points. So this one, not a function. I get this one, the third graph, and they're asking me to determine if it's a function. Well, apply your vertical line test. Notice no matter what vertical line I draw, they all meet the graph only once, right? So this one, yes, it is a function. All right, so vertical line test. Now, quickly apply this vertical line test so we can go over the evaluation of functions, right? So I'm going to give you some examples quickly and we will move on. Figure out if this is the graph of a function or not. All right, first number 8. Write in the chat your answer. Based on the vertical line test. Eugene, very good. Julie, very good. Excellent. Yeah, great, guys. If you apply the vertical line test to this parabola, you will notice that no matter what vertical line you draw, they all meet this parabola just once, right? Once. So then this one, yes. Excellent. So it's a function. What about number 9? So we can move on to this number 9 now. I see. Eugene, very good. Yuji, Julie, very good. Yeah. Clara, very good, and welcome. The guys who joined, just joined, that you are all welcome, guys, all welcome, okay? I will always let you in. If you're using your name and you're in my roster, I will let you in. Great. Okay, so look, Very good, guys. If you apply the vertical line test to this graph that looks like a snake, right? Here, good, right? One point for each vertical line. But in general, when you get to this part, look, 1, 2, 3, 3 intersections, right, with the graph. This is not good, right? So this is going to fail the vertical line test. So no, right? Big no, not a function. Excellent, excellent. This one, I leave it for you to do at home, this table, right? Figure it out. We're going to move to evaluation of functions now, which is a little bit computational. All right, let's go ahead with that. Evaluation of functions here. We're going to deal with this type of exercises, but let me give you some background here. It turns out functions can be evaluated, right? The input value can be evaluated so that you can get the output value. How? We do it via direct substitution. Direct substitution. What is a direct substitution, Professor? Well, here is an example. It's very simple. Suppose your function is defined by this rule x squared minus 3x plus 1. This rule is telling you that you have to square the input value, whatever it is, then multiply by 3 and subtract that result from x squared and then add 1, right? Add 1. So they say compute f of 4, compute f of -2, and compute f of -x. Let's start with the easiest part, compute f of 4. What will be f of 4? Well, notice that this x is just a placeholder, really, placeholder. I'm going to write here, it's a very important idea here. Notice x is just a placeholder for the input value, right? So if I substitute x with 4, wherever I see x, I put 4 instead. Of course, I have to get the answer, the output value, right? Yeah, so there you go. So this is 4 squared, 16. This is 12. 12 minus, subtracted from 16 is 4, plus 1. Plus 1 is just 5, right? 5. Now, in case the numbers are not friendly, right? Are not friendly, could be in your homework or maybe on the examinations, right? I was able to do this in my mind, right? But in cases the numbers are big, heavy, difficult to deal with, use your calculator. We have our Desmos scientific calculator, or use any scientific calculator you have at hand, right? And do this. Square minus 3 times 4 plus 1, right? I'm using parentheses to emphasize the fact that x is just a placeholder, right? Yeah, I got 5, right? Now, notice, if I do the same with -2, I can simply copy and paste this here. And instead of 4, since x is just a placeholder, if I write -2, then I should get my output value, right? For input value -2, look, it's going to be 11. So 11 is what we're going to write here, right? So again, -2 squared, -3 times -2, all that 11 here. And the same for this guy, right? But the difference here now is that this is no longer a number. It's just, it's a variable, right? But no problem, because we said that x is a placeholder, right? It's saying square the input. The input is this minus x. Allow me to use a different color. So we're going to square minus x here, square minus x, and then -3 should multiply the input again, but the input is minus x, right? So now simply do this, right? Minus x squared minus 1 squared is 1, right? So it's x squared. Simplify, right? -3 times -x, positive 3x, right? And plus 1, right? That's it. This is the answer, okay? Okay, great. So this is when it comes to evaluate functions. So I want you to try now to evaluate functions. If you're dealing with numbers, you can use your calculator. If you're dealing with variables, you have to simplify it algebraically, right? So let's try, for instance, this guy, the first one. Try this out. Make it bigger if you don't see it well, right? And remember, hint, f of x is defined as this. X is just a placeholder, so think about it, right? Sometimes it's useful to write parentheses, just ready for the input value, right? So yes, try to do the first one, please, and let me know what you get. Let's see. Eugene. Very good, very good. Excellent, excellent. Lucero, also great, great, very good, guys. Yeah, very good, right? They want F of 2, right? F of 2. More students. Yeah, Clara, also very good. Excellent, excellent, guys. They want F of 2, right? They want F of 2. So we're gonna do F of 2. That's how you read it. And that should be 2 squared plus 3 times 2 minus 7. 3 squared is 4. 3 times 2 is 6. 6 plus 4, 10. 10 minus 7 is just 3, right? 3. So we're talking about this guy, right? Now, if the numbers are heavy or difficult to deal with, use your calculator. I explain how, right? Now, let's do this with symbols. Now they say that this is the function. Can you figure out now this one, number 2? F of x equal negative 2x squared plus 3 times x plus 3. And they are asking you to do f evaluated at negative x. Hint, notice x is just a placeholder, right? It's telling you, this function is telling you whatever the input is square it, here multiply it by 3, and then simplify, right? As we did before. I see students figure this out. A little bit tricky, but doable. Let's see. Jing, you made my day. QG, excellent. Very good, guys. Excellent. Yeah, I need to do some algebra here, right? So f evaluated at minus x will be, remember, first you deal with exponent. What is negative x squared? Look, negative 1 squared is positive 1, right? Positive 1. And this is just x squared. This negative 2 stays outside. Positive 3 times negative x is negative 3x, right? Negative 3x plus 3. I no longer need parentheses, so this could be written just this way, right? Minus 3x plus 3. And then we're done. This is it. This should be it. So answer, guys, this guy, right? Excellent. There are some functions here defined with absolute values. We'll see. Yeah, this one should be okay. I'll leave it for you, number 3, but I want you to try number 4. They say f of x is equal to, this bars means absolute value. Remember, for you to recall, absolute value, right? And the absolute value operator just makes the number positive, right? Whatever the number is will come out positive. That's what it does. They are asking you to evaluate this function at negative 9, right? So place inside here negative 9. So do this. Can you try that? Yeah, go ahead. Now let's practice, guys. Practice makes the master. When you post your answer, you don't have to be right all the time, right? But what is important, guys, is that you participate and we make sense of these things together here, right? That's what I'm here for. Yeah, Jing. Let's see, let's check. Great, yeah, good to know. Thank you. Yeah, Julie, Clara, Eugene. Excellent, guys. I think you figured this out. Excellent. Yeah, very good. If we take the absolute value of negative 9, remember the absolute value, all it does is it makes the number positive. So this guy, absolute value, that's how you read this, absolute value negative 9, is going to be just the number 9. I'm highlighting this for you to see when you study. And 9 minus 6 is just 3, right? 3. Excellent. Excellent. Mm-hmm. Yeah. Mm-hmm. Yeah, excellent, excellent. Great. Now, maybe we can try, yeah, I want to do this one too, because sometimes the negative sign matters. So try to do this and then we will move on. Do this. F of x is equal to this. Figure out f of minus x. F of minus x, right? Figure this out. This is f of x. F of minus x. Remember, x is just a placeholder, so you gotta do this, right? Placeholder x, so wherever you see x, you substitute negative x instead, because that's our input value. So figure this out. Yeah, and try to recall this for your homework, guys. Homework number 1 is already there, so you're going to use all these tricks there. And of course, if you cannot figure it out, send me an email. I will help you out. Yeah, great. Can. Eugene, Clara, very good, guys. Very good. Excellent, excellent, excellent. Yeah, excellent, excellent. Yeah, this on the top is just minus x, right? But on the bottom, negative x squared. Remember, the square is going to make this negative 1, this invisible negative 1 that is in there, positive, right? Negative 1 squared positive. So this will be x squared. So positive x squared plus 5. And this guy is represented here, right? Yeah. Excellent. Now, let's do this one, the one over here. Yeah, there's 2, and then we will move on. Okay, try to do number 7 now. F of x is this. They're asking you to do f evaluated at 2x. And remember, the hint is going to be x is a placeholder, right? So place parentheses there, and inside the parentheses, write your 2x, right? A lot of algebra there, but doable, right? Doable. Just simplify, do your algebra there. 7. Clara, very good. Excellent, excellent. Jing, great, great. Hughie, Khan. Very good, guys. Very good. Yeah, excellent, excellent. So notice exponents always first, right? Before multiplication. Remember pandas and all that stuff that you learned before? Yeah, exponent first. So this will be what? 2 here waiting, but this 2 square is 4, right? 2 times 4, and this x square should be x square. Now I have 4 times 2x here plus 2. If you are not familiar with these things, do it slowly so you don't make mistakes. 2 times 4, 8 now, 8x squared, minus negative 4 times 2, 8x, plus 2, right? Plus 2. And that is this guy. Number 7, this guy. Excellent. This one I will leave it for you to do at home. It's similar. Try this. This is going to be important for your homework and for the examinations also. Look, this guy. What would be f of x plus h? And when you take calculus, you're going to see this guy x plus h again when you do derivatives and stuff. So it's a nice exercise, this one. It's going to be a little bit long, but it's good to understand what is the evaluation of this function at this input value, x plus h. So we got to do this, right? So try to work this out. Hint, work out first this exponent, right? This is x plus 2, x plus h, sorry, times x plus h. You have to FOIL this out, right? FOIL this out. So try to FOIL this out. And then distribute property must be followed here, right? And then minus 2. Try to work this out. is a big result, but it is what it is, right? So yeah, let's check. Let's check. Yeah, it's the answers are divided into groups, but I think Lucero, yeah, you made my day, Lucero. I think you got it right. Clara also, yeah, very good. Hugh G. Yeah, it's long and painful, but it's just algebra, guys. Okay, yeah, let's explain. Let's do it together, and probably to reinforce, we can do number 10 as well. All right, but let me explain this, right? Look, I supposed to square this binomial, right? But how do I square binomials? I cannot just distribute exponent. That is no rule that says that I can distribute over a sum, right? So I gotta FOIL this out. I gotta write this x plus h times x plus h. This is what this is, right? This part. Now here is easy because it's twice x plus twice h, right? Distributive property minus 2. But now here is where the painful part is, the foiling out, right? And notice there is a minus 2 waiting there, right? Minus 2 waiting there. So we gotta be careful there. I would suggest use a big parenthesis here to deal with this part, okay? So look, x times x is x squared. X times h is xh. H times x is the same as x times h, right? Commutative property for multiplication. So allow me to write it as x times h, right? The same as h times x. And finally, h times h is h squared. But this guy must be within parentheses because it's the result of all this, right? Maybe even to be precise, look, let's highlight this and show that the result of that is this, right? There is a negative 2 waiting there, right? So you gotta take into consideration too. So plus twice x plus twice h minus 2 from here, right? This is this is this. Now distribute negative 2 over negative 2x squared. But before you do that, let's do this slowly, right? So that we can all follow. Look, notice that these two are what mathematicians call like terms. 1xh plus 1xh is twice xh, twice xh. This plus h squared plus 2x plus 2h minus 2. Finally, I distribute now. Negative twice x squared, negative 2 times negative 2, negative 4xh. This guy times this guy, minus 2h squared, plus 2x plus 2h minus 2. And now look through. If you find like terms, combine them. But turns out here there are no like terms, right? This is like apple, this is like orange, this is like strawberry. No like terms. So conclusion, leave it alone. Leave it alone. That is the final answer. So which matches perfectly with this, right? Minus 2x squared minus 4x times h minus 2h squared plus 2x plus 2h minus 2. Advice, guys, when you deal with multiple choice questions, compare term by term, sign by sign. The choices, they look alike, right? So make sure you pick the right answer. So this is this. Now I think we should go over the last part. But before we go over the last part, perhaps you should do this one. This is much easier, but you should do it. Try this. The function is this, minus 2x plus 5 over 5x plus 6. And they are giving you this challenge, find f of x plus h, right? And hint, wherever you see x, you should write instead x plus h, right? So you're gonna do this, 5x plus h plus 6. Yeah, try to do that and figure out what's the answer. And then we will move to the last part, which is one-to-one functions. A lot of students are posting answer, which is great. Very good. Jin Lucero, I think Julie, Clara, Yuji, Lucero. Yeah, excellent, guys. Very good, right? Here, no square, so I just apply my distributive property, negative 2x minus 2h plus 5 on the top. On the bottom, 5x plus 5h plus 6. And that's it, right? This is it. And this is a perfect match with choice A. Excellent, excellent, guys. All right, let's go over the last part. It deals with these super special functions called one-to-one functions. A one-to-one function is a function in which each output value corresponds to exactly one input value. Okay, these are super special functions. It allows us to put two sets in what is called one-to-one correspondence, right? Which is very important, especially when you are trying to identify things. Example, if you have in one set people, John, Eva, Paul, on the other set, driver license number. Look, each of these guys have a unique driver license number, right? Uniquely associated to each people. So this sets what is called a one-to-one correspondence between these two sets, right? So it's very important, this type of functions, because the arrows, they go like this, like parallel to each other, kind of. Not necessarily parallel, but better said, for each input value, exactly one output value, but also for each output value, exactly one input value, right? And these are important functions because they can be reverse, right? For each driver license number, a unique person, people, and for each person, a unique driver license number, right? Great. Now, mathematical example. Cubic function. The cubic function turns out to be a one-to-one function. I will show you why. If you allow yourself to have as input value 0, 1, 2, -1, -2, and you use this rule, you associate with each number here its corresponding cubes. So 2 cubed is 2 times 2, 4 times 2, 8. 1 cube, 1 times 1, 1 times 1, 1. 0 cube, 0 times 0, 0 times 0. Negative 1 cube. Negative 1 cube is, believe it or not, guys, negative 1. Negative 2 cube, negative 8. Sometimes the students ask me, Professor, negative 2 cube, negative 8. Explain. All right, here is the explanation. One explanation is this, right? Negative 2 cube means negative 2 times negative 2 times negative 2. This guy is positive 2 times negative 2, ends up being negative negative 4, sorry, here, positive 4 times negative 2, negative 8, right? Negative 8. Great, negative 8. Now, guys, if you want to make sure that this is the case, right, when you're dealing with exponentiation of negative numbers, if you have doubts, that's not a problem because we have a Desmos scientific calculator here that we can always use, right? Negative 2 cube for cube, you gotta use this and write the exponent on the top. Negative 2 cube, negative 8, right? There we go. Okay, now if you write the output values here and you pair them up with the input values, you're gonna get the following. 0 is paired up with 0 is here. 1 is paired up with itself 1. Negative 1 now is paired up with negative 1 down here. 2 is paired up with 8 all the way up here. Negative 2 is paired up with negative 8 all the way down here, right? Suppose here is negative 8. And let's just do it. It was there, yeah, let's erase this. Okay, so then if you connect these points that we got with a smooth curve, what you're gonna get is the following. You will see. It looks like a chair where we sit when we are tired, right? A chair. I gotta be careful here. Yeah, and I'm gonna call this a chair-like function. The representation of the quadratic function turned out to be a parabola, right? This one, let's call it chair-like function, okay? Chair-like, right? Because it looks like a chair where we sit, right? Now, mathematicians, when they look at this representation, they notice the following. They notice that if we draw now not vertical lines, but horizontal lines now, horizontal lines, look, horizontal line here, another horizontal line here. We notice that these horizontal lines, they meet the graph only once. No matter where you draw your horizontal line, look, they meet the graph only once. So mathematicians realize that this is an intrinsic feature of one-to-one functions, right? So they came out with this rule. It's called the horizontal line test. And it says that a graph represents a one-to-one function if and only if all horizontal lines intersect the graph at most once. Okay, so this test serves to identify if a function is one-to-one, right? The vertical line test serves to identify if the graph is a function, but this goes farther. Once you know that it's a function, if you want to know that it is a special function, if it's a one-to-one function, you draw horizontal lines, right? And if they meet the graph only once, then yes, it is a one-to-one function. Otherwise, no. In order for you to practice, guys, I have these worksheets, where we're gonna go over all of these guys. Yeah, let me do the first one here sort of to explain, right? Is this a one-to-one function? Let's use the horizontal line test, right? If I draw horizontal lines, notice no matter where I do it, I find always just one point of intersection with the graph. Then this means yes, it is a one-to-one function. One-to-one function, right? Great. Can you try number 2? Is this a one-to-one function? Right, same question. Try to figure this out for number 2. Very good, guys. Yeah, and by the way, this is, let's just mark here as f of x equal x cubed, right? The cubic function has this graph always chair-like. Yeah, one more thing, right? If you wanna confirm that this is the shape of a cubic function, I explained to you guys, right? Use your tools. We have Desmos scientific calculator, but also we have this Desmos graphing calculator, right? So for example, I want to check that this is the shape of a cubic function. Well, I can write y equal x cubed, or equivalently f of x equal x cubed. It's the same thing. And there the chair appears, right? You see it? Chair-like function for f of x equal x cubed, right? There we go. Always use your tools, guys, to confirm your knowledge, to check your knowledge. Everything should make sense, right? Good. All right, so answer for number 2. Is this a one-to-one function or not? You see? Aha. Lucero, very good. Very good. Julie, Jinling, no, great, excellent, excellent, right? Yeah, they are giving me this parabola that opens downward, right? Downward. Now, they are asking me to check if it is Clara. Very good, also, very good, excellent. They are asking me, always be careful with the question, right? They are not asking me to determine if this is a function. With vertical line test, this would be a function, right? But the question is it a one-to-one function? Is it that this is a special function, one-to-one function? For one-to-one function, use to determine this, use the horizontal line test, right? Horizontal line test. So when you see one-to-one function, immediately you have to use the horizontal line test. Now, notice if I draw horizontal lines, look, in general, they meet the graph twice, right? This is not a one-to-one function. It's a two-to-one function, perhaps, but not a one-to-one function, right? Two-to-one, perhaps. Yeah, now, excellent, excellent. Not one-to-one. It's a function, though, right? But it's not one-to-one function. That's what is important. Number 3, can you try this? It's a little bit tricky. Do this one now. Number 3, I'm going to make it bigger. Is this a one-to-one function? Yeah, try, give it a shot, guys. Yeah, here we're here to learn. Julie. Julie. Very good, very good. You got it. Julie, do you mind to explain why this is not one-to-one? In the chat or verbally? Yeah, Jing also, right? Anyone who posted an answer, could you guys explain why this is not one-to-one?
It fails the horizontal line test.
Excellent, excellent, excellent. Very good. Doesn't pass the horizontal line test, right? Because when you draw the horizontal lines, notice, look, 2 points of intersection. 2 points of intersection. Professor, what about this line? This is special line, 1 point of intersection. Yeah, 1 point of intersection here, but in general, look, this is 2 points of intersection, 2 points of intersection. So this means no, not a one-to-one function. Excellent, great. Yeah, let's check more here. This one is a tricky one. Let's see if you can figure this out. Is this one-to-one function? Is this a 1-to-1 function? And try to remember this for your homework. Let's see. Activity on the chat room. Very good, Jing, Julie, Khan, very good. Anyone who answered this question, could you guys explain why this is one-to-one? Or write something on the chat? Very good, Julie. It passes the horizontal line test, right? Very good. It passes the horizontal line test. Excellent, excellent, right? Look, notice this is look like a snake, right? But what is important is when you draw horizontal lines, look, no matter what horizontal line you draw, the horizontal lines, they will meet the curve just once, right? So then, yes, it is a 1-to-1 function. Excellent, excellent. Yeah, I think this one, two more. Yeah, this one. What about this? Is it a 1-to-1 function based on the horizontal line test? UG, Emily, very good. Very good. Yeah, Jin, Kan, very good, right? Yeah, since they are asking me to determine if this is a 1-to-1 function, immediately I think of the horizontal line test, right? Horizontal line test, look here, professor is meeting at the curve at once. Yeah, but you gotta go in general, right? You gotta check if that happens in general. Not here, look, 3 points of intersection here, 3 points of intersection here. So because of this, right? Even though here it meets the curve only once, but because of this part, no, it is not a 1-to-1 function. Great. Now let's go over the last one, which is a bit tricky. Yeah, this one. Let's finish with this, and I will give you some hints, and we will wrap it up. Do this one, number 6, please. Is it a 1-to-1 function? Very good, very good. Activity in the chat. Clara, yes. Emily, very good. Eugene, Julie, yeah, excellent. Clara, can you explain why this is a 1-to-1 function? Will you type something on the chat, or you can say verbally? It passes the horizontal line test. Very good, guys. Very good. Excellent, right? It passes the horizontal line test. Professor, this graph is broken in 2 parts. Does it pass the horizontal line test? Yes, because notice, if I draw horizontal lines, notice 1 point of intersection. No matter where you draw the horizontal line, 1 point of intersection, right? But what about here? Well, even there, right? And this is separated from that. So next horizontal line probably here. All the horizontal lines meet the graph only once. So this is, yes, 1-to-1 function, right? This was no. Excellent, guys. Excellent. Okay, now, before we go, let me just tell you something very important in web work. So let me bring you to web work.